Let's talk about directional derivatives and the gradient vector. For purposes of this discussion, let's first of all let z equal f of xy. Let's let x be a function of t, and let's let y be a function of t. Let's also let P be the point in the xy plane, x sub 0, y sub 0, where x of t sub 0 is equal to x sub 0, and y of t sub 0 is equal to y sub 0. Also, let u hat be the unit vector with scalar components u1 and u2. Now recall that since z is a function of x and y are both functions of t, z is actually a function of t, so we can take its derivative with respect to t at the point where t is equal to t sub 0 using the chain rule. And the chain rule gives the derivative as dz dt equals the partial of f with respect to x at p times dx dt, and that's at t naught, plus the partial of f with respect to y at p times dy dt at t sub 0. Now this chain rule can be written as a dot product of two vectors. One vector with components the partial derivative of f with respect to x at p and the partial derivative of the partial derivative of f with respect to y at p, and the second vector with components dx dt and dy dt. So dz dt can be written as the dot product of these two vectors. The first has components the partial of f with respect to x at p and the partial of f with respect to y at p, and the second vector has components the derivative of x with respect to t and the derivative of y with respect to t. Now this vector that has components partial of f with respect to x and partial of f with respect to y is called the gradient vector. And we have some notation for the gradient vector. We have this symbol, that's del. So we read this del f of p, and this is defined as the vector with components f sub x at p and f sub y at p. So we take the gradient of the scalar function f and get this thing we call the gradient vector. Now suppose that L is a line through P parallel to the unit vector u, and T is directed distance from P to some other point on the line L, call it Q. You say at some point Q that has coordinates X and Y. And T is the directed distance along this line from P to Q. Well, then the displacement vector from P to Q if T is positive, has magnitude T and direction given by U hat. So the displacement vector from P to Q is T times U hat. But writing this equation in component form, the components of the displacement vector from P to Q are x minus x sub 0 and y minus y sub 0, and the components of T times U hat are TU1 and TU2. So saying these latest two vectors are equal is the same thing as saying that their components are equal, and that gives us that x minus x sub 0 is T times U1, or x of T is equal to x sub 0 plus T times U1, and similarly we get that y of T is y sub 0 plus T times U2. But then dx dt is equal to U1, and dy dt is equal to U2. So the chain rule gives us dz dt is f sub x, the vector with components, f sub x at P, f sub y at P, dotted with our unit vector has components U1 and U2. Or we can say that dz dt is del f at P dotted with our unit vector U hat. Now this derivative with respect to distance parallel to U, this derivative of f at P with respect to sine distance parallel to U is called the directional derivative of f at P in the direction of the unit vector U hat. So we give it special notation that indicates that. We call it f sub U hat at P, and it is del f at P dotted with U hat. And this gives us the instantaneous rate at which f is changing at the point P when points in the domain of f are allowed to move in the direction of the unit vector U. This gives us the instantaneous rate of change with respect to the distance moved in the direction of U. Now here's where things get interesting. If f is a particular function and P is a particular fixed point in the domain of f, and we talk about this directional derivative in the direction of U hat, the way we get different values of the derivative is by changing the direction. In other words, changing the U hat. Well, one of these directions will make this directional derivative have its biggest value. In other words, make the rate of increase be the biggest it can be, rate of increase at P. And one of these directions will make the directional derivative have its smallest value, its most negative value. And that will give us the greatest rate of decrease in f at P. Well, the way we figure out what these directions of max rate of increase and decrease are is we express the directional derivative of f, and given in the dot product above here, in its angle form. Okay, so del f at p dot u is magnitude of del f at p times magnitude of u, but that's 1, and then times cosine of theta, where theta is the angle between del f at p and u hat. Well, clearly, magnitude of del f at p times cosine of theta has its biggest value when cosine of theta is 1, which happens when theta is 0, which tells us that the u hat we're using has the same direction as the gradient vector. And this directional derivative will have its smallest value when cosine of theta is -1, and that happens when theta is pi, which tells us that the u hat we're using has direction opposite the gradient vector. Okay, so what we have here is that the max value of f sub u hat at p is the magnitude of the gradient vector at p, and it occurs in the direction of u hat equals del f at p divided by the magnitude of del f at p. And the minimum value of the directional derivative at p is the negative of the magnitude of del f at p. And the direction that gives us that minimum value is in the direction of u hat equals the negative of del f at p divided by magnitude of del f at p. Here's an example. Suppose that z is equal to x squared plus y squared, and p is the point 1, 1. Then del z at p is the vector with components 2 times x, when x is 1, will be the first component, that's 2. And then the second component will be 2 times y, when y is 1, so that's also 2. And let's suppose that we want the directional derivative of z in the direction of u hat. Let's find z sub u hat at this given point p at a particular u hat. Let's go ahead and give u hat. Let's say u hat is the unit vector with components 2, 3 divided by its magnitude, which would be square root of 13, I believe. Yeah. Well, we just use our formula that we derived for the directional derivative, that being del z at p dot u hat. Okay, so that would be the vector with components 2 and 2 dotted with our unit vector. Which is going to give us 4 over square root of 13 plus 6 over square root of 13, which gives us 10 over square root of 13. Okay, so this is the instantaneous rate of change of z equals x squared plus y squared at 1, 1 with respect to distance moved in the direction of this given unit vector. Now let's find the maximum value of the directional derivative at p. Well, we know from what we just did a little earlier that the maximum value of z sub u hat at p is the magnitude of del z at p. But that's the square root of 4 plus 4, which is 2 square root of 2. And this maximum value of the directional derivative will occur in the direction of del z. We leave it up to you to find the minimum value of the directional derivative at p and the direction in which it occurs. Now let's discuss some properties and uses of gradient vectors. Suppose that f of xy equals c is a level curve of z equals f of xy. So this is a curve in the domain of f of xy such that any point coming off this curve being plugged into the function produces the function value c. So as the inputs xy are allowed to change, as long as they stay on the curve c, as long as they stay on the curve f of xy equals c, the value of the function f of xy will stay constant at value c. Now suppose that P is a point on the level curve This is that P we were talking about earlier with coordinates x0 and y0. And also suppose that x equals x of t and y equals y of t are parametric equations for the level curve. With x of t sub 0 equals x sub 0 and y of t sub 0 equals y sub 0. Then if we take the derivative with respect to t, of each side of the equation, f of xy equals c, we get the derivative with respect to t of f of xy equals the derivative with respect to t of c, and that's going to give us that the partial of f with respect to x times dx dt plus the partial of f with respect to y times dy dt is equal to 0 at this point where t is equal to t sub 0. But written as a dot product, this says that del f at p dotted with this vector that has components dx dt and dy dt at t naught is equal to 0. That dot product is equal to 0. Well, the vector with components dx dt and dy dt at t sub 0 is tangent to the curve at point P. And this dot product being 0 says that the gradient vector is perpendicular to this tangent vector. Therefore, the gradient vector is perpendicular to this level curve. Okay, so del f at P is perpendicular to the level curve of z equals f of xy and goes through P, and this is happening at P. Okay, so now we have an idea of what the gradient vector looks like. We already know that the maximum value of the directional derivative, the greatest rate of increase of the function at a point, is occurring in the direction of the gradient vector. So we know the gradient vector points in the direction of increasing function values, but we now also know that it's perpendicular to the level curve through P at P. Okay, so say your level curve looked like this, and say you had a function value of, say, 2 on this level curve, and then you had another level curve here, function value 3 on it, another level curve here with, say, function value 4, and then function values getting smaller going the other way, let's say. Well, then that means that the gradient vector at P has to be perpendicular to this level curve through P, also point in the direction of increasing function value, so it would look something like this. And of course, the negative of the gradient vector would point the other way, opposite direction. Okay, so we now know what del f looks like. We also see that a use of this gradient vector is to find a vector that's parallel to the normal line through the level curve at point P. Now, when we start talking about relative extrema, functions of two variables, z equals f of xy, we recall from Calculus 1 that for a function of a single variable, if there's a relative extreme value at the point x equals a, then x equals a is a critical number where the first derivative is either 0 or undefined. So if we were to take z equals f of xy and fix y and allow x to change, if we have a relative extreme value at xy equals ab, then we know that the derivative with respect to x at ab has to be 0. So the partial derivative of f with respect to x at ab would be 0. And similarly, if we fix x at a and allow y to change, if we have a relative extreme value at ab, then the derivative of f with respect to y at ab would have to be 0. So the partial of f with respect to y at ab would have to be 0. Okay, so what this tells us is that if we have a relative extreme value at ab, then, and the derivatives exist, f sub x and f sub y exist, then they would both have to be equal to 0 at ab. So the gradient vector would have to be 0. And of course, another way that we can have a relative extreme value is for the gradient vector to be undefined. We could have a sharp corner, some kind of peak or cusp type thing. So when we were looking for relative extrema of z equals f of x, y, we set del f equal to the zero vector, or find points that make it undefined. These are going to be called critical points. And then we have the second partials test that we can use to test the critical points to see if we have relative extreme values or saddle points there. And of course, if that second partials test fails, we have to use some other technique. Now we can extend what we've done for functions of 2 variables to functions of 3 variables. So if we have a function w equals f of x, y, z, then we can talk about del f for this function as being the vector whose components are f sub x, f sub y, and f sub z. Now, of course, you're doing this at a point, x naught, y naught, z naught. So the definition is a direct extension of what we did when we had a function of 2 variables. And the properties of the gradient vector relative to level curves for functions of 2 variables extend to properties that apply to the relationship between the gradient vector and level surfaces for functions of 3 variables. In other words, del f is normal to the level surface of w equals f of x, y, z. That goes through the point P and this is happening at P. And this gives us a way to find a normal vector for the tangent plane to a surface at a point P. If the surface is given as f of x, y, z equals c, we just treat that as a level surface of a function of 3 variables, w equals f of x, y, z equals c. And then the a normal vector for the tangent plane will be del f at P. Here's an example. Suppose we want to find tangent plane to z equals f of xy at the point P, which has coordinates x naught and y naught. Well, we know that to find a plane, we need a point and a normal vector. Well, our tangent plane that we're looking for touches the surface z equals f of xy at the point x sub 0, y sub 0, and z sub 0. Let's call this the solution. So our known point on the plane that we're looking for is x sub 0, y sub 0, and z sub 0. Now, to find a normal vector at our point, what we'll do is treat our surface as a level surface of a function of three variables. So our surface z equals f of xy, we can say is a level surface of the function w equals big F of xyz, which is equal to little f of xy minus z. So if we consider the function of three variables, w equals big F of xyz, which is defined as being little f of xy minus z, our surface is the level surface on which the values of the function big F stay fixed at 0. So we can take the gradient of big F at x naught, y naught, z naught, and that will be our normal vector for our tangent plane. So our normal vector, a normal vector, let's call it n, is del f, del big F, at x naught, y naught, z naught. But the components of del big F are big F sub x at x naught, y naught, z naught, big F sub y at x naught, y naught, z naught, and big F sub z at x naught, y naught, z naught. But the partial of big F with respect to x is little f sub x I'm taking that at x naught, y naught. And the partial of big F with respect to y is little f sub y at x naught, y naught. And the partial of big F with respect to z is negative 1. So we have our normal vector has components f sub x, f sub y, and negative 1, all taken at x naught, y naught. So our tangent plane is f sub x at P times x minus x sub 0 plus f sub y at P times y minus y sub 0 plus negative 1 times z minus z sub 0 equals 0. And we can solve this equation for z to get z is equal to z sub 0 plus f sub x at P times x minus x sub 0 plus f sub y at p times y minus y sub 0. And that's an equation for our tangent plane. And we can see that this is pretty much a direct extension of the tangent line that we found in Calculus 1. It has the same form. I think that's enough for now. Oh, well, before I sign off, just let me mention that for a function of 3 variables, we also have the directional derivative of the function of 3 variables. Directional derivative, it's specified in the direction of a unit vector u hat at a point x sub 0, y sub 0, z sub 0. The definition is the same that it was for a function of 2 variables as far as being the dot product of the gradient vector, del f, and the unit vector u hat. And you can use the same type of analysis that we did before. Write this dot product as magnitude of del f times magnitude of u times cosine of theta, and make the conclusion that the maximum value of the directional derivative is the magnitude of the gradient vector and occurs in the direction of the gradient vector, and the minimum value is the negative of the magnitude of the gradient vector and occurs in the opposite direction of the gradient vector. Okay, that's it for now.